Okay, so we're going to look at another example of using the force analysis problem in an equilibrium, but a dynamic equilibrium. And we're going to use your book again, the example out of your book, to show you some differences in process and empower you to be able to do this on your own with the process that we've outlined. Okay, so this is example 6.2. It reads, a car with a weight of 15,000 newtons is being towed up a 20-degree slope at a constant velocity. Friction is negligible. The tow rope is rated at 6,000 newtons maximum tension. Will it break? So we are going to look at this process, look at the process we've dealt with, and examine it based on that process. So step number 1 is to identify the object. So in this case, it's a car, and it's being towed up that hill. Now we want to identify a picture, represent a picture in this example. So here is our hill, and maybe here's our car, and it's being towed by a rope in that direction up the hill. And I forgot the angle already. It's at a 20-degree slope. Now we did talk about looking at the magnitude of the acceleration. And in this case, the acceleration is equal to 0. So we could use one of two coordinate systems. We could use a coordinate system that's aligned with the tow rope, and then if we did that, then we're only really looking for the magnitude of the force in line with that coordinate system. Or we could look at a Cartesian coordinate system, and then we'd have two components to that tow rope. So as we think about a coordinate system, we want to think about what's going to make our life the easiest. In this case, since I'm interested in the tension of that rope, I know it's rating, but I don't know what it actually is. Well, then I might want to align my coordinate system with that rope. So this is what we call a rotated coordinate system. I'm identifying the horizontal as this along the angle, and my vertical along, of course, the vertical. So this I'm going to call horizontal prime. It's not our typical thing that we think about with horizontal. And this is going to be vertical prime for that same reason. It's typically not what we think of vertically, but in this case, we can identify it as a vertical-like representation. Okay, so we have our coordinate system. I'm not looking at motion, so I don't need to set an origin. We certainly could do that. We will in the next problem. What are my interactions? Okay, so, well, the force of gravity is acting on the car. So we have the force of gravity. That's between the car and the earth, and that does act vertical, straight up and down. We also have the tow rope. It's a tension, and that's between the car and the rope. And that's acting along the ramp. Now the car is sitting on a ramp, so we certainly have the normal force. So that's going to be between the car and the ramp. And remember, the normal force is perpendicular to the contact. So if the ramp is angled at this 20 degrees, our normal force is going to be pointing up and to the left. Now we're told friction is negligible, so we don't have a frictional force acting on this car. And I think that's it. Those are all our forces. So I drew the interactions separate this time. Let's look at that free body diagram. So here is our car, and we have the force of gravity on our free body diagram. Remember, that's equal to mg. We have the normal, or the tension, it's along the slope. And we have the normal force that is perpendicular to that slope. So those are the three forces acting on the object. Now I've chosen to do a rotated coordinate system, again, remember, because I want to find t. And so I don't need to worry about t having multiple components. If I align the coordinate system with that tension, then it only has a component along the coordinate system. So it'll make solving the problem a little bit more efficient. Okay, so we're going to separate now into our h prime and our vertical prime. Again, I'm only calling them primes to help us recognize that it is a rotated coordinate system. So separating our forces in there to their horizontal and vertical components with respect to h prime and vertical prime. So I number them 1, 2, and 3, and we'll look at the forces in turn. So force number 1, that's our force of gravity. Now, it has in our prime coordinate system 2 components, a horizontal component and a vertical component. So it's going to be helpful for us to see how that angle is developed. Where is my 20 degrees with respect to that force of gravity. Let's imagine if our plane, if our ramp, was straight, flat, horizontal, it would look like this. Now, to get it to an angle, I rotate my straight up and down by 20 degrees. So it looks like this normally, and I'm going to, here's my horizontal, I'm going to make that into an angle. Horizontal rotates by 20 degrees. This becomes my 20 degrees here. Okay? So work with those rotations, that's tricky. All right, if that's my 20 degrees, opposite is along the horizontal prime. Let's keep in mind, this is horizontal prime. This is vertical prime. Opposite is along horizontal prime, so it's going to be the sine of the angle. So I have mg times the sine of my 20 degrees, which our mass, we are told, is, we're given the weight. So my mg is 15,000 times the sine of 20. It's a very squeaky marker. 15,000 times the sine of 20 gives me 5,130. That's a positive value. Is the horizontal component a positive value? No, it's pointing in the negative direction of that component. So I need to recognize that this is 5,130 in the negative direction, 51,000, or 5,130 in the negative direction. Vertically, my vertical component is going to be 15,000 times the cosine of 20. So it's adjacent, and 15,000 cosine of 20 gives me 14,095. So 14,100. It's giving me a positive value. It's pointing in the downward direction relative to my rotated axis, so I need to remember, and I need to tell them that we need new markers in here. 100 should be negative. All right, we're going to abandon blue for a while. So that's my force of gravity force, broken up into the horizontal prime and vertical prime components. What about my tension? That's force number 2. Well, it is only along the horizontal prime. It has no component vertically. Is it positive or negative? Well, it's pointing in the positive direction as I've defined it, so it's positive. That's all I got. I don't know its value. And force number 3. Well, force number 3 is pointing along the vertical, and it's pointing up in a positive direction relative to that new prime. It doesn't have anything in the horizontal. So here's my 3 forces separated into vertical and horizontal components. All right, now I add them together and apply Newton's second law. So remember, Newton's second law says the sum of the forces horizontal, in this case it's prime, is equal to mass times acceleration horizontal prime. And if I'm not changing my motion, constant velocity, I'm 0 along that ramp. Vertically is the sum of the forces vertically, prime, is equal to the mass times the vertical acceleration, and it's a vertical prime acceleration. And in this case, I'm not changing my motion up and down off that ramp. So it too is 0. So I can now apply that principle of Newton's second law, where I have minus 5130 plus t plus 0 is going to be equal to, this is the sum of my forces in the prime horizontal direction, well, those are equal to 0. Similarly, the sum of my forces in the prime vertical direction are negative 14,100 plus the normal force, and those are equal to 0. Now this problem is asking, does the rope break? What tension is the rope? Well, I'm going to solve for T. T is equal to 5,130 newtons. It's rated at 6,000 newtons. So we are good for towing. I don't need to worry about that side. It's not part of what I'm interested in. That's it. So again, following that process, In this case, we rotated the axis to make our lives a little bit easier. Had we not, we would have had components of the normal force and components of the tension, and we would have had a little tricky time solving for the problem. So sometimes we have to rotate our coordinate system so that we can solve it. And since we were wanted to identify the tension, and that's in line with the rotated ramp, rotating the coordinate system works well. Okay, good job.